Alrighty, hello everyone. I am doing a little video lesson today so that you are not going to be falling behind if you missed the lesson on Friday. Yes, I already said on Friday that I was going to come in before the wrestling meet. That was not a lie. I am here before the wrestling meet. Just wanting to get this done and out of the way so you can have it for the weekend. This is for you geometry kids. This is the similarity unit. Alright, but we're talking about that geometric mean. Most of you have already been through this with me. I'm like half awake as well, so we'll see how this even goes. All right, let's go through these warm-ups again because solving these ratios was exactly the purpose of doing the geometric mean was the entire purpose of doing these because they are virtually identical, okay? Our entire goal here is to get the x's alone. The x's are introverts and they want to be with nobody but themselves, just like me, okay? So I am going to get rid of, first, I need to make sure I get rid of the x's that are underneath the division line, okay? If it's underneath this division line, we want to get rid of those stat. And how do we do that? We do the opposite of what's going on, okay? It's being divided by x minus 3, so I want to multiply this because that's the opposite of divide. We're going to multiply this by x minus 3. I like to write it as x minus 3 over 1 because that gives us a fraction, and it's way better to work fractions with fractions and whole numbers with whole numbers. Why bother mixing them when you can just throw it over 1? Now it's a fraction. It's as easy as it gets. All right, when you're multiplying fractions and you have identical things across from each other, they're gone. Identical, identical, gone. Okay, eliminated. That leaves us just 7 over 1. So we have 10 over x equals 7 over 1. But crucially, perhaps the most important thing that I could say, we need to do that to both sides. You can do anything you want to an equation. You can multiply it by x minus 3 over 1, absolutely. But you gotta do it to both sides. All right, so I need to make sure I do it to this side now, times x minus 3 over 1. Nothing is identical. Sure, there are x's on both of these across. That does not mean that they're identical because this has a minus 3. They are no longer identical. Nothing cancels. So we just multiply across. That means we must multiply this x by 10, giving us 10x. We must multiply this negative 3 by the 10. That gives us negative 30. And that puts us over x. That puts us over 1 times x. I don't need the 1 though, because 1x and x are the same thing. All right, that equals 7 over 1. Again, I don't need to write 7 over 1 because 7 over 1 is just 7, right? And that's the whole purpose of putting it over 1. I mean, we can put it over 1 eventually, or originally, it just wound up that way conveniently, okay? We still have another x that's underneath. X's underneath are no bueno. We get rid of them. Multiply by x over 1. Identical, identical, cancel. That leaves us finally, well, almost finally, with 10x minus 30 equals, gotta do that x to both sides, equals 7x. Now we're pretty close to done, all right? There's two ways you could go about it from here. The way that I do it just by instinct, okay, this does not mean it's the best way, it's just my instinct, is to get rid of 7x on this side just to make all the x's together, okay? 10x minus 7x leaves us with 3x minus 30. Hey, there's nothing on this side, so let's say it equals 0. That's true. There's nothing else on that side. Nothing. 0 checks out, okay? Last two steps, add 30. Add 30. We got 3x equals 30. Let's cancel. Equals 30. X is still not alone. X is being touched by 3. Touch is times. Touch is times. You've heard me say that quite a bit. Touch is times. Okay, so if it's touching the x, that is times. We do the opposite, which is divide. Opposite, divide. Finally, x equals 10. And boom goes the dynamite. That's it. All right, over here, we're gonna do the same thing. Why start with this x when it's closer to being acceptable? All right, if the x is on top, even if it's not alone, if the x is on top, even if it's not alone, that's a whole lot better than being underneath the division line. So I want this one gone first. Okay, x over 1, same thing, cancel. 8 over 1 equals 8, leaving us with x over 2 equals 8 over 1, or just 8. Must multiply this by x over 1. X times x is not 2x. X times x is x squared. X times x is x squared. 1 times 2 is 2, equals 8. All right, gotta get rid of that 2. I'm gonna do that before the squared root. I mean, I don't really know exactly how to explain why that's so much better, other than if you do the square root first, your life will be miserable, okay? So just do this before doing the square root. Times 2 over 1, cancel. Times 2, okay? I'm kind of all over the place here, but you're following, I'm sure. Well, you better read. X squared equals 16. 8 times 2 is 16. Still not alone, still not alone, still not alone. X is the square root of 16. Now, I know that I harp on and on and on and on and on about not giving me decimals, okay, and keeping it as the radical. This is an exception. This radical doesn't create a decimal. The square root of 16 is 4, so I do want the answer of 4, okay? Number 3 is going to be a different case. Number 3, you know what? Let's give you a shortcut right now. Let's go ahead and pull out the shortcut, because we are going to use that shortcut all the time during the geometric mean. Why do these 4,000 steps when there's a shortcut of this times this equals this times this? This times this equals this times this. X times x equals 6 times 7. X times x equals 6 times 7. X times x equals 6 times 7. X times x is x squared. 6 times 7 is 42. Square root, square root. Now this would be a decimal. This would be a gross decimal. It's going to be somewhere, it's going to be 6 point something, okay? But leave it as the radical, because this is more accurate than the decimal will ever be. It includes all of the decimals. You do not have to write or round, because this includes them. So keep your answer like that. All right, let's erase this board real quick. Hey, take a minute. I forget, unlike real life, you can just pause. So I am just going to erase it. I don't really have a time crunch. I'll admit, I didn't just come in this morning to make the video. I'm also going to spend like 30 minutes sitting in the staff room massage chair. But might as well be somewhat productive while I'm here. All right. So we aren't going to really do this, all right? We did it in class. It's not going to be as useful as a video lesson, okay? Because this was highly experimental. This I will talk about. The whole purpose of this lesson was to talk about creating an altitude in the triangle and using that altitude as a geometric mean tool to find other things, okay? Same with using the legs as the hypotenuse leg theorem, but that's only possible by making that altitude. We'll go into that more later. The altitude, okay, it is going, if you take a right triangle, it can be any orientation. It can be like this. This works. All right, you could still make an altitude. I'll do it in a minute and you'll see why that's more difficult. But if you can have the right triangle so that it's twisted and sitting on its hypotenuse, kind of looking like a mountain or a pyramid or something, that makes the altitude real easy to draw. All right, you go from that 90-degree angle, that vertex, and you just draw a line straight down, meaning that it becomes perpendicular to the hypotenuse, creating a 90-degree angle there. Okay, that's what perpendicular is. All right, this is our altitude. Let's say it creates a point, B, or D, sorry, D. That looks not like a D with the way that I wrote it. Okay, with point D. What this slide is kind of asking us to do, or the next one, I'll go back, is to name the right triangles in the figure. We got one. I see a right triangle right here. Okay, ADC. I also see CDB. Notice that I did not call it, I'm being specific about my naming. All right, I'm going from the top vertex point, okay, to the 90-degree angle, to the furthest away point. Notice how this end is shorter than this end. Okay, I'm going down the short end to the 90-degree angle, through the long end, okay, and then traveling the hypotenuse with my naming. A, D, C. I guess I wouldn't travel the hypotenuse because I'm not going to call it ADCA, right? But A, D, C. So for this triangle, I'm not going DBC, I'm not going BCD. I need to make sure I'm going CDB. Let's write these. Triangle ADC and CDB, and triangle CDB. We also have one more, by the way, but this one we're not really going to use basically much at all. And that's the original one, right? That's, let's see, how would I be doing that one in that same sense? It would be the short end, so yes, it would be ACB. ACB of the overall big one. Why is that A? Triangle CDB. Triangle ACB. I'm going to erase this one because I don't want to use it for visualization's sake. I do want to use this one for visualization's sake. So as we know, when you have appropriately named triangles, you can see what side correlates with what. AD correlates to CD. DC correlates to DB. Oh look, AD correlates to CD. DC correlates to DB. So one thing I forgot to tell you, just because we talked about it in class, one thing that I'm not having us prove, and you're just going to take my word for it, you're going to trust me and believe me, is that when you make an altitude, you've created three similar triangles. Three triangles that always have the same ratio of sides. Okay, so what that would be saying is that side AD, divided by side DC, is equal to the equivalence of this triangle. The equivalence in this triangle were CD, okay, equals CD over DB. CD over DB. Okay, so we've created ratios. These are similar, so you could absolutely solve for any of these sides if you were given, let's see, 2 pieces of information total. That's pretty great. So name the right triangles, we kind of did that. We're not doing part 3. We didn't even do that in class. We didn't do this because I told you that they're all similar. But this I have right here. Okay, write the corresponding sides of each pair of triangles as proportions. That's what we got right here. This looks a lot like what we did in the warm-up, except it doesn't have numbers and letters like the warm-up did. All right, well, here's the actual theorem that proves that I'm not just spouting nonsense. It proves that what I said was true. If an altitude is drawn to the hypotenuse of a right triangle, okay, if an altitude is drawn from the vertex to the hypotenuse of a right triangle, then the two triangles formed are similar to both each other and the big triangle that you originally started with. Now this leads us into a very important point. This leads us into our geometric mean. Erasing. Now a geometric mean is going to be a little confusing the way I teach it up front, okay, at the start. Because I am always going to call, no matter what the variable is in the question, I'm going to call the geometric mean x. Even if we have x as a variable, okay, it's going to be different from the x that I use in the geometric mean. Now the reason that I'm specific about that is because the geometric mean involves a formula that we will always use under all circumstances for this topic. This formula will not change. The position in the triangle of A, X, and B could be different depending upon what we need to do or what we're trying to solve for. But this is always still the same. Okay, what the geometric mean is is it's the geometric mean, okay, that was a really stupid way to say it, of two positive numbers, okay, x is the geometric mean of two different positive numbers, something like side lengths, okay, or dimensions, a and b. All right, now if that seems a little confusing, let's actually kind of see it. Okay, let's see it in this right triangle altitude hypotenuse theorem. Let's draw a better triangle here because we're going to use this quite a bit. All right, this is a right triangle popped onto its hypotenuse. The measure of the altitude, let's draw that just so we have it available. The measure of the altitude drawn from the vertex of the right triangle to its hypotenuse is the geometric mean. The altitude is the geometric mean between two other things. Let's get that. This is the geometric mean. When you are trying to solve for parts of the hypotenuse or the altitude itself, this position, this thing, this altitude is always our x position. That is not the variable. Okay, maybe we're given a number here. Maybe we're given 2 and something else is x. Maybe this is x. That does not mean that this goes here. Whatever is in this position always goes where x is. And remember, a over x equals x over b. A over x equals x over b. A over x equals x over b. All right? But what about a and b? What are they? Okay, that's what they're saying here is the geometric mean between the measures of the two segments of the hypotenuse. Okay, we have two new segments of the hypotenuse. It was split up. It was split up by the altitude. One of them is A, one of them is B. Okay, I always make A the shorter one. I don't really care though. Like, either will work. That's the point. Okay, but I do prefer this being the A. And now look, that sets us up for A over X equals X over B. If I have two of these, I could not, let's say that I had these two. Let's say that I had 2 and 6, okay, as A and B. I had 2 and 6 here in the hypotenuse. I couldn't use the Pythagorean theorem to find anything. However, I could use a combination of these theorems to find every other piece of this triangle without the Pythagorean theorem. And quite frankly, way faster than the Pythagorean theorem. Significantly such. All right? So this is the hypotenuse theorem. This helps you find, especially if you're given this, let's say 3, and you're given this as just x. Actually, let's do this. I want to do this one because this lets you see that x is not this x. Okay, I really want to make that clear. This x is a variable. This is what we're solving for. This is not our geometric mean, x. All right? I don't make the letters. I don't decide the letters. It's not my problem. So, I'm just trying to make sure that you don't fall into that trap. All right? So this is our x position, this is our A position, and this is our B position. So let's fill this out. A over x equals x over B. A 2 over x 3. I know, tricky. I know. Over x 3 equals the sometimes I'll just say geometric mean to make it easier, right? A over the geometric mean equals the geometric mean over B or x, okay? Now we could solve for x. We could not do that with the Pythagorean theorem. We could not do that with the distance formula. The only way we can do that is with this geometric mean setup. All right, let's get rid of the x times x times x. And gives us 2x over 3 equals 3 times 3. Okay, 2x equals 9. Divide by 2, divide by 2. 2 is touching the x, touch times. Okay, so we're going to divide by 2. X is 4.5. I mean, I made up those numbers and everything, so whatever. But all right, I'm erasing it because you can pause a video. Can't pause me in real life, even though I know that you all wish you could. Even I wish I could pause me sometimes, but all right. Let's look at it a little bit differently. I'm gonna leave up exactly how I had it originally, so you can see how I change it for this other theorem. All right, A, B, X. For this other theorem, it is similar, but in my opinion, actually even more useful, right? If the altitude is drawn to the hypotenuse of a right triangle, each leg, this is a leg, this is a leg. In a right triangle, you got two legs and a hypotenuse. The hypotenuse is always longer than each of the individual legs. That's how you can distinguish it. You don't need to really differentiate these two legs, all right? Maybe give them different variables, that's it. But it doesn't really matter which one is which. Well, I shouldn't say that. It doesn't matter which one you choose to work with at any given time. You'll see what I mean. Each leg of the right triangle. Individually, you don't do them both at the same time. You pick one, you do that one, then you can do another, all right? Each leg, let's say this leg, let's call this leg 1 and this leg 2, okay? Each leg, or leg 1 of the right triangle, is the geometric mean. The leg is the geometric mean position. It is that x position now. The x position is no longer here. When you're using the leg theorem, the x position is one of the legs at any given time, okay? Now the A and B, the two positive numbers that you're working with, are the hypotenuse itself, that is A, okay? Not any segment individually, but the whole thing, all right? So you would have to add up the two segments if it's not given to you. If you're given something like 2 and 6, the A would be 8, because 2 plus 6 is 8, and it's the whole thing. The whole thing is the A. That's always the case, okay? No matter which leg you're working with, A is always the whole thing. However, B changes determined or depending upon which leg you are working with. If you're working with this leg, then this section and only this section of the hypotenuse is B. Okay, not this part, just this part. If you're working with this leg, it would still be the whole thing is A, but this section would be B, okay? It's saying that it is the geometric mean of the hypotenuse as a whole and the segment of the hypotenuse adjacent, next to, closest to the leg, all right? So let's go with this leg first. What would that actually look like? Let's put in some numbers. Let's say you are given, let's say that you're trying to find the leg length. Okay, that'll make it a little bit trickier this time for us. You're given that, well, let's really spice it up. You're given just the hypotenuse, okay? It is 2 and 6, like I had mentioned earlier. Okay, if your hypotenuse segments are 2 and 6, then the total length of the hypotenuse would be 8. So A would be 8. If this is our geometric mean, then 2 would be the B. A position, B position, geometric mean position. Let's set it up. A over X equals X over B. A over X equals, ooh, I made a great problem here. This one's gonna turn out real nice. Okay, equals X position over B, which is 2. Let's skip ahead and do the shortcut this time. Let's solve it with that nice shortcut. 8 times 2 equals X times X. 8 times 2 equals X times X. 8 times 2 equals X times X. 8 times 2 is 16. X times X is not 2X. I hear that way too often. It is not 2X, it is X squared. Square root, square root. Yes, I do want the number for this because it is clean and not a decimal. It is 4. Told you I made a good problem there off the cuff. I didn't know it was going to turn out that well. All right, I'm gonna skip the worked example because you can just pause the video right now and read it. But I am going to do one last example for you all, and that will be it. Maybe this will help you with your homework assignment. Yes. I'm hoping some of your parents are watching this video, not just you, so they can call you out that you got homework this weekend. Page 505 and 506, parents. That's what's due. Page 505 and 506. All right, over here. This is a typical problem that we're going to be working with. However, most of your examples you'll work with won't make you name all three of these. Okay, you won't have to go through all three. This time we will. We're going to solve for all three using just this little bit of information. This is all we got. That's impossible to use distance formula, Pythagorean to get anything else here. Except we do have the tools to use the geometric mean. All right, so we got, let's start here. Let's start here with the hypotenuse theorem. X is conveniently X. X is conveniently X. It's also the X position. This is also the X position or the geometric mean. Okay? Now again, you can make either or your A. It doesn't matter. I like the smaller number as the A. Does not matter. Okay, that is my B. And boom goes the dynamite. That's going to be easy. X or A over X equals X over B. A over X equals X over B. Shortcut. 5 times 10 equals X times X. 5 times 10 equals X times X. 5 times 10 is 50. X times X is X squared, not 2X. X squared. Square root. This is a gross. All three of these solutions are going to be gross numbers. I don't want anything but the radical on all three of these answers, all right? Square root of 50. That is X. Now, a lot of people in class, and I thought this was fascinating, a lot of people in class got that answer and their instinct instantly went to, okay, so I can just solve for y with 10 squared plus the square root of 50 squared equals y squared. That would work. Yes, absolutely. Same on the other side. But I'm going to show you what's a lot faster, like significantly faster. Okay, let's make this our next side we work with. X, Y, Z. We'll go in alphabetical order. Now remember, as a variable, yes, this is y. We are going to write y as we solve. We will be not using x here, we will be using y. But the y is in, I know this is confusing. The y is in the x position, all right? It will be in the x position because it is the geometric mean. So, if I have a over x equals x over b, first of all, remember, I need to change my a and b when I'm dealing with legs. When dealing with legs, our a and b changes. A is the total hypotenuse. A is the whole shebang, all right? 10 plus 5 makes the whole thing 15. If we're dealing with this side, the leg or the hypotenuse segment closest to this is 10. 5 is further away, so we're not using that. We're using 10 as our B. So the whole thing is A, 10 is our B. That is in our X position. Y is in our X position. So let's draw it out. A, 15, over X, which is Y, equals X, which is Y, over B, which is 10. Shortcut, 15 times 10 equals y times y. 15 times 10, if you're using the calculator for this, stop. I got a trick. You multiply by 10, okay, and then push it together. It's 150. You're just adding a 0 on when you're multiplying by 10, 150. Y times y is not 2y. It's y squared. Square root, also gross. It's just y is the square root of 150. Excuse me. All right, last thing before I'll be quiet and let you enjoy your weekend. Z. Z is also going to be an X position. However, A remains 15. B switches to the side closest to our geometric mean. We got it there. And we rewrite. A over X equals X over B. 15 over X position of Z. Z equals Z over 5. Shortcut. 15 times 5 equals z times z. 15 times 5 is 75. Z times z is not 2z. It is z squared, square root. Z is the square root of 75. Also a gross number, leave it like that. All right, you guys. Hopefully that gives you enough tools. Wish luck to the boys wrestling team. Congratulate the girls wrestling team. Not girls. Well, yes, them too. But the girls basketball team, because they had one of the best high school games I've ever watched in my life last night. That was amazing. Both teams. Congrats. And I'll see you Monday.